Hello everyone, this is Dr. Zach, and for today's lesson preview, you were to use separation of variables in order to solve for y. So if you haven't had a chance to do that, please do it now. Once you separated your variables, you should have found that the natural log of the absolute value of y was equal to k times t. Now, you need a plus c on your problem. From here, we're about ready to solve for y. We're going to rewrite each as an exponential function, and we get the absolute value of y is equal to e to the kt plus c. Now, once we use our rules that deal with exponential functions, let's drop that c down in front, and we can write y equals c e to the kt. You might ask yourself, where did the absolute value go? But we know that an absolute value means that you could have a positive or a negative. And since c has not been defined yet, c takes on the value of either a positive or a negative. You're given an initial value that y at 0 is equal to y naught. So when we substitute, we know that y naught is equal to c e to the 0. So we now know that c must be equal to y naught. Finish up your problem by substituting the c value back in. We know that y equals y naught e to the kt. So that is going to be solving using separation of variables, something that you should be fairly good at. So we began with a differential equation. Now, a differential equation relates one or more functions and their derivatives. Your differential equation defines that relationship between the function and the rates of change. So for example 1, I have dy over dx is equal to 2x minus 1. So we want to solve this for y, and we know that our solution has an initial value of 2, 1. So if we solve this for y, let's again separate the variables. We will have dx divided by the 2x minus 1 is equal to dy. Integrate both sides of this equation, which leaves us with a natural log on the left side. But notice, if we let u equal 2x minus 1, du is going to be equal to 2 dx. So when we substitute in our dx, we're going to have a multiplier of 1/2 the antiderivative 1 over our u du. And on the right hand side, the antiderivative of dy is going to be y. And I could put the plus c over there, but I'm going to solve for the y, so I'm going to leave it on the left hand side. So now I have 1/2 the natural log of the absolute value of u, but u in this problem is 2x minus 1. Add my plus c, so that must be equal to y. But we're told in this problem that we're traveling through the point 2, 1. So when x is equal to 2, the y value is equal to 1. 1/2 the natural log of, put in our 2, we're going to have 3, plus c is going to be equal to 1. And that tells us that c is going to be 1 minus, let's do the natural log, 3 to the 1/2 power, so that's the square root of 3. Rewrite your problem because we were told specifically to solve for y. So y must be equal to, let's write the natural log, the square root of 2x minus 1, and then our c value is going to be plus 1 minus the natural log root 3. But you know what? We could get just a little bit fancier there. That square root of 3 could be part of our problem with the natural logs. We're going to do a combination. We will have the natural log, the square root of our 2x minus 1 over 3, and then outside of the argument for the natural log, we put plus 1. Now, the reason I wanted to write it this way is to remind you that as you're looking at your problems, you might have to rearrange your expressions using your log rules. For example 2, you're asked to draw a slope field. Now, it's been a while since you've drawn a slope field, but be reminded of what you will need to do. You're given a set of points, and on these points, we want to fill in values. So, for example, if x is 0 and y is 0, dy dx is 0 plus 0, which will make it a nice horizontal line through 0, 0. If you exploit some of the things that are happening, 1 and negative 1, well, when we add x and y, that will also give us 0. So if we follow 1, down 1, again, we're going to have a horizontal line. And that gives us a nice little diagonal that we could draw through our slope fields. Now fill in 1, 0. If we do that, 1 plus 0 is going to be 1. So at 1, 0, the slope is 1. Next, we want to think perhaps where else might we have a slope of 1? What about at 2, negative 1? So if we went right 2 and down 1, we have another slope of 1. And look at this. We're going to draw parallel lines along that diagonal again. Now, what happens at the point 1, 1? Our slope is 2, which makes it steeper. Check and see if I put in 2, 0, the slope should be 2. And again, we're going to exploit the idea that along that diagonal, they will be the same. As we move right, our slopes are getting steeper because the next diagonal, they're all 3, then 4. And by the time we're at the edge of the slope field, these are very steep as we go towards the left. Now, what happens let's look at negative 1, 0. At negative 1, 0, the slope is negative 1. So following the diagonal, similar things happen. Notice this looks like it might be an asymptote as we go across our field. What about negative 2, 0? So at negative 2, 0, the slope is going to be down 2 over 1. So it's a steeper negative value along the next diagonal. And then as we move left, once again, we're going to keep our slopes steep in a negative direction. Here we go. All right. Now, for the next part of the problem, it says we want to graph a solution that's traveling through 2, 1. So go find your 2, 1 and sketch in your solution. Follow what your slopes are doing. Remember, as you are passing through the diagonal, you're going to be a little bit horizontal right about here where I'm drawing an arrow. And then I have this asymptote that I'm going to follow as I head towards the left part of my graph. So these were quick reminders on how to solve an integration problem using separation of variables and how to draw slope fields. As I look at example 2 again, I don't believe I'm going to be able to separate my x and y, and that's perhaps why we were not asked to actually solve this integral. So example 3 asks us to solve the ODE with the given initial condition. ODE represents an ordinary differential equation. So we're going to use separation of variables to solve this problem. We will have dy over our y squared is going to be equal to 7x to the third dx. That now we're going to be able to integrate since we have separated our variables. When we integrate the left side, we're going to get 1 over y with a negative in front. It's going to be equal to our 7 over 4, x to the fourth. I'm going to add c to the right-hand side. Now we should solve for c. We're going to substitute 3 in for your y values. Negative 1/3 is going to be equal to 7 over 4. Substitute the 2 in for your x. So that's times 16 plus c. So we now have 28 on the right-hand side. So negative 28 and 1/3 is going to be equal to our c value. Now from here, we're going to rewrite our problem so that negative 1 over y is going to be equal to your 7 over 4 x to the fourth power plus, and then your c value. Let's see here, we're going to have negative 28 and 1/3. Let's do a little bit of cross multiplication. -1 over your 7/4 x to the 4th minus 28 and 1/3 is going to be equal to our y value. All right, and of course you could simplify by multiplying by 12 over 12 so that you have a little bit nicer expression for y. Example 4, this time you're given a slope field and asked to sketch the graph that satisfies the equation f(1) equals -1. So that is the point 1, -1. Now, as you work through these problems, make certain that you are using the scales that are written here. You can see this is going to 2.5. So I'll go right 1, down 1, double check. Oops, this is where we're going to start. So we have the value 1, -1. As we follow the path, make certain that you are going to get the slopes in correctly as you go along. Make certain you're horizontal where you need it to be, and then head downward. So it looks a bit like a cubic for this function. Now, notice that I put some arrows on the ends of mine. Don't put arrows on the ends of your graphs. The AP does not want arrows. They just want you to stop the graph where you run out of space. So for question number 1, given your slope field, sketch your graph. Number 2, sketch your graph, and then you'll be able to work on the lesson practice. So please sketch your graphs and then compare them to what I've drawn. Take a look at your work. Make certain you are once again starting at the correct values for each of your graphs. That's it for today's lesson. Go ahead and complete the lesson follow-up.